Okay, so let's do a very quick review of the previous two presentations. We talked about using a model to model data, and this model can be used to predict future data. The example we used was housing size and house and prices. And we developed a model with two parameters that can be mathematically described as a line. And the values of these two parameters determine the goodness of fit. Right? And then we continued and talked about the cost function, right? The cost function reflects how good the fit is. We obtained this least squares cost function and motivated that. And multiplied by a constant, nothing changed. And that's what we call J. And this J is a function of two variables, theta 1 and theta 2. And we want to find the values of theta 1 and theta 2 that minimize this cost function. So we talked about how that looks graphically. We had developed this graphical representation of the cost function as a function of two variables. It looks kind of like a bowl. And we can represent also using contour lines. And the shape of this cost function may be quite irregular, and sometimes it may not be so nice. We can actually do the same thing in multi-dimensions, which we'll get to later. But now we're at the point where we ask the question, how can we find the best solution? The best solution graphically is right here, but how can we find it mathematically or computationally? Right? So we're going to introduce a method called gradient descent that enables us to iteratively find the best solution for the problem, which means to minimize the cost function. So we start with an analogy. Suppose we're in a mountainous region and we want to find the lowest valley. We want to get down as low as possible. So, and suppose furthermore that we're blindfolded. So we can't see far away. We only know where we are locally. So for instance, if the person is standing right here, he can tell the slope that he's standing on. He can tell which direction is down, which direction is up. If he wants to get to the lowest point, which direction should he go in? Well, if he can tell what slope he's on, of course he should go down. Okay? So let's see what that looks like graphically. Remember our cost function. Here we have a more complicated cost function that has peaks and valleys. So imagine the person on this surface. This is our situation mathematically. We may start with a particular value. For instance, suppose we start with theta 0 equal 0.7 and theta 1 equal 0.4. So we'd be roughly about here. Okay, so we start with some guess and we want to improve our guess. So that's what an iterative method does. It starts with an initial value and it improves it. Now if I start here and I want to improve it, then I would head downward. Right? So that's the entire idea behind gradient descent. Now, if I go downward, if I go in a fixed direction and I go downward, it may or may not continue to go downward. For instance, if I go downward in this direction, then I may end up going upward. So what you do is you go downward for a small distance and then you reevaluate because the downward direction may change. Okay? So you go downward for a small distance, then reevaluate, then go downward again, then reevaluate, and so on. Right, so this process is summarized here. Initialize theta 0 and theta 1 to some random values using your best preliminary knowledge. Continuously make updates to these variables in the direction of descent, that is, go downward, and then keep going until you can't go downwards anymore. All right, so let's see what that looks like. Okay. So suppose we start at theta 0 equals 0.7, theta 1 equals 0.4. It's that point there. If we go downward, you can see we go downward for a small distance and the downward direction has changed. So we go in the new downward direction. Then here again we have another, go in this direction, the downward direction has changed, right? You see that we have to turn to keep going downward, and keep going downward, 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 until we reach the bottom. Once we reach the bottom, there's no more downward direction, so we're finished. That will give us our final result. All right, very simple idea. And the mathematics is not too complicated. Now, we could possibly start at a different point. There's no particular reason why I started at that point. That was just a random choice. Suppose you choose a different starting point. Well, then the result will be different. And unfortunately, in this case, the final point that I end up at is not quite as far down as here. So this illustrates a very fundamental problem in finding optimum solutions is it's difficult to distinguish between the overall optimum and a local optimum. This is what you call a local optimum. I can't improve locally from this point. To improve from this point, I would have to go back up again, right? This one is globally optimal. It's the best of all local optima. And the big challenge with optimization is to get to the global optimum and not get stuck in a local optimum, right? So, fortunately, in the case of linear regression, there's only one local optimum, which is also the global optimum. All right, so let's see how this translates mathematically. Well, let's look first at the simple case where we set one of the variables, theta 0 equal to 0. And we're just trying to find the best value of theta 1. Now, of course, that may not fit the data best overall, but let's do our best with a single variable theta 1. All right, so here we have three different values of theta 1, 3, 1, and 0.5. And depending on where our data is, the data is not actually shown in this picture, but depending on where the data is, the value of j will be different. Now in this case, our j depends only on theta 1, theta 0 is 0. So here we have a function of one variable, and we're trying to minimize this function. You may recognize this as a quadratic function. And in fact, you can minimize this using calculus. But we want to show this general numerical method, which works not just on quadratic functions, but on arbitrary functions. So it turns out in this case that our function j will look like a parabola. Now it won't always go all the way down to 0. This is just one example case. But in fact, in general, the linear regression problem does have a parabolic shape. So if we start at this point, if we start at this value for theta 1, right, what's the direction of decrease? Well, if you only have one variable, there's only two directions. You go to the right or to the left. So it's pretty obvious I want to go to the right. Now, the other question is, how far do I go to the right? And that's what we're going to discuss as this presentation unfolds. Right? So you can see here, if I'm at this point, I have a slope, actually quite a steep slope. So as it says here, the slope is large and negative. So it's clear that a negative slope indicates a step in the positive direction. Now here we say it's large. Just hold that thought. The large is going to influence the size of the step, but we'll get there later. Okay? So here we go down in this direction. We take a step to the right. And if we take a step to the right, and we evaluate the value, so just to be more specific here, I can take my pen here. So, right, I started at this point, right, and the value of the function was up here, and then I moved to this point on theta 0 axis, and when I evaluate the function, I'm up here, right? So the value is much smaller, so we certainly have improved. Now, can we improve more? Sure. I still have a negative slope, which still indicates a step in the positive direction. So I take another step, and just to note, the slope is moderate and negative. Right, so I take another step, and I get here. Right, the slope is still negative. I take another step in the positive direction, and this was kind of fortunate that I ended up right at the right point, but I was certainly going in the right direction. So at this point, the slope is flat. Now, do I go to the right or to the left? Well, it really is, there's really no indication of going one way or the other. When I reach a flat slope, then I stop the process, because if I go either way, I will get bigger. Now, it's possible that the parabola was inverted. If the parabola is inverted, I wouldn't have reached this point anyway. Right? The fact that I reached this point down here follows from the fact that I was following in a downward direction. There's no way I could follow in a downward direction and achieve a peak. Okay? So once I reach the zero gradient, or the zero derivative, I'm done. Okay? Now, all of this depended upon the starting point. And there's nothing magic about the starting point. I could start anywhere. Suppose, for instance, instead I had started on the other side. In this case, I have a slope that's large and positive. Now, positive slope indicates that I want to move in a negative theta 1 direction. I want to decrease theta 1. So I go decrease theta 1, and here now I have, you're going to see that this is basically the mirror reflection of the other side, right? It's basically doing the same thing, but I am coming from the other end. But here I'm going to still take a negative step, and here I'm still going to take a negative step. And now here he took a negative step and overstepped. Now if I overstep, then the slope becomes, I'm sorry, this was a positive slope. This is a positive slope. So I go here, and so if I overstep, I'm going to get a negative slope, which indicates I want to step back in the positive direction. The sign of the slope is opposite the sign of the step. So if I happen to end up here with a negative slope, I'm going to take a positive step. Okay. Right now, so I mentioned that the size of the slope indicates something about the size of the step. Now, in this case, because the slope is large and positive, I expect that I can take a relatively large step and still be going negative. Why is that? Because if the slope is large and positive, here it's becoming less and less positive as we go along. Here, let me change my pointer so you can see what I'm doing. It's becoming less and less positive as I go along. But if it's large and positive, that means it's going to take quite a while to start to even out to zero. So if I have a large slope, I can probably get away with a large step. Now, not always. It's possible that I might have a large slope which bottoms out very quickly. But the general indication is if the slope is large and positive, it's going to take a while for the slope to bottom out. Now, some of you may be familiar with Newton's method of finding roots, which is a little bit similar to this, but it's not quite the same. Newton's method for finding roots has a different formula, and you're trying to find where the function crosses the axis, and not where the function is minimum. So this does resemble Newton's method, but it's not exactly the same. Now, in Newton's, I mentioned that because in Newton's method, you do not subtract a large positive number when the derivative is large. The subtraction depends on both the derivative and the value of the function. But that's not the case here. So if you don't know about Newton's method, you can ignore the remarks I just made. But there is a difference between Newton's method for finding roots and the current method for finding a minimum. Right? So as I said, if the slope is large and positive, that indicates a relatively large step in a negative theta 1 direction. So as the slope becomes more moderate, we take a more moderate step in order not to overstep. Right? If I take a step that's too large, I'm going to end up on the other side. Right? So here I'm going to subtract by a small positive number. Because if I subtract by a large positive number, I'm going to get on the other side. Right? So here, I don't know where to go. We're done. Okay, as I said, if the slope is 0, then if I go either way, I'm going to increase the value of the function. All right, so this is just to repeat the same thing. I don't need to go through these steps in detail. All right, so we're going to mathematically specify the algorithm that we just specified basically heuristically. All right, so that will be in the next video, and tune in next time.